then I'll start. So yeah, my talk is about generative modeling for high-energy physics. And so let me just quickly start from some actually examples of recent advances in deep learning, in generative modeling using deep learning. So for example, there's this website called this X does not exist. If you follow it, there's a lot of examples where deep learning based generative models were used to produce well, it's mostly images, it's some realistically looking images. And so if you just follow that size, that website, and just look at examples, if you haven't seen such things before, you might get really impressed about what this technology allows you to do with generating images. Now, another another notable example is these things related with style transfers. Again, you can apply deep learning to transfer an image from one style to another and produce really nice artistic effects on those images. And then if you try to track the history of how well these models were performing, we kind of started this whole boom, this whole explosion of different models. In my opinion, started in 2014 with a Goodfellow model, with Goodfellow work about generative adversarial networks. And then if you follow how those got better and better from year to year, just in a few years, these got really impressive, showing really realistically looking images. So now, how is this related to high-energy physics? So here on this right side of this slide, I'm showing you the expected CPU usage as it's expected to be used by the LHCb collaboration. We have here these bars showing the expected amounts of CPU usage in this or that year. And although this was made like 2 years ago, and so now all these plans are probably shifted by the COVID, still the general idea still holds that we'll need quite a lot of computing resources, and a good fraction of those resources will be dedicated to simulating, to producing our Monte Carlo simulations. And so this particular bar plots corresponds to the case if we were using the 100% detailed simulation, so the one that uses GANT4 and all the accurate algorithms. And of course, even with this scenario, here this red line shows you the expected amount of available resources, and so we're well beyond that. And as far as I understand, the situation is similar for other experiments as well. So it's very important to develop fast simulation models. And so now speaking about these generative models, what if we instead of generating images, instead of generating people's faces, we train those models to generate detector responses? Now, if you look what happens under the hood in those models, then single object generation is typically just a single forward pass through the neural network. And with if you use modern GPUs, you're able to parallelize that, and you can in a fraction of a second you can generate millions and millions of such objects. So this is a very good candidate for if you are able to train such models to produce realistically looking detector responses. This is a good candidate for fast simulation models. So having done this introduction, here's the outline of what I want to cover today. So I want to start from just discussing what is the problem setup for this generative modeling. I wanted to make an introduction about two of the commonly used models, basically generative adversarial networks and variational autoencoders. Of course, there are many more than this, but like I probably won't have time to introduce like a lot of them. But I hope these two are at least worth introduction. And the level of introduction I'm about to give is I expect that people are familiar with at least like simple supervised deep learning, and probably not familiar with this model. So hopefully it will be understandable for this kind of level knowledge. And so after having introduced the models, I'm just going to show you several applications where, well, mostly GANs were used for fast simulation, and have some discussion about that, I hope. So let's dive right into it. So about generative modeling. So in this, in the problem setup is this follows. You have some training data. This is basically a set of objects, and here I'm just denoting it like this. And these objects, they can be anything, like photos of people, animals, or whatever. It can be text, can be audio. But for us, for people from high-energy physics, experimental high-energy physics, the most the most interesting option is where these objects are some signals, some responses from a high-energy physics experiment detector. And now our goal is to build a model to sample similar data. So what do we mean by this? So what we mean is that there exists some population probability density, and these objects that are given to us, those are sampled independently, and they are identically distributed according to this probability density. And so what we want to do is we want to learn some, well, here I denote as Q of x, so some other possibly parametric distribution. We want to bring it as close as possible to this population PDF, even though we don't know this population. We only know, like, we only have samples from it. Okay, so now describing one of the solutions to this problem, namely generative adversarial networks, or as a short for GANs. So how, let's try to answer the question, how can a neural network generate data? So we know that a neural network is this kind of like, well, at least for the simple cases like these feed-forward networks, you have some kind of input, you transform it in several steps, and then you get some output. And what's important, like, is that all those transformations are differentiable, so we can later train this model using backpropagation algorithms. So a simple way to generate data with this setup is to basically, as an input, you can plug some random noise. So here it's called some variable z that you take distributed according to some fixed distribution, and you can choose the distribution. This can, for example, be normal distribution with unit mean and zero mean and unit variance. Typically, you would take not just a single variable, but you would take a multi-dimensional, multivariate normal distribution, or not necessarily normal, but typically you want to take multiple inputs in here, and then you transform that to some kind of output. And well, this output here this output is just a function of the input, and it is distributed to some kind of distribution which you want to train to optimize to be to be similar to the distribution of the data. So the important part about this setup is what I said, is that this output, this x prime, is a differentiable function of the parameters of your network. So if you had a measure of similarity between these objects and the objects from your training data set, you would be able to optimize it with gradient descent. So how can you find such measure? For this kind of model, the approach it's called adversarial approach. It's actually quite simple. So how could you define a similarity between two distributions of objects? Well, basically, if your objects are indistinguishable, if they are similar, if they are distributed under same distribution, you're not able to distinguish between them. And so it's a natural thing to try to train a separate model to distinguish between the real, like the training data, and the data that you have generated. And so for this purpose, we introduce another network. It's called the Discriminator network, which takes as input either generated data or the data from the training set, and just tries to separate them, just optimize some separation metrics like likelihood, cross entropy. And then, since everything here is differentiable functions, you can then take this measure of separation that your discriminator is optimizing, and you can optimize it in the opposite direction with respect to the parameters of the generator. And as it's shown in this original paper, in the limit, so you have like this kind of two-player game. You want to maximize separation with these parameters and then minimize it with these parameters. If you find a saddle point in this two-player game, then this optimum would correspond to generator generating basically objects that are indistinguishable from your training data. So typically, this means that you need to optimize the same thing in two opposite directions. And in practice, it's typically done in steps. So in practice, typically you start from you sample some data from your generator, you sample from data from your training sample, you do a few steps. So you have this discriminator loop. You have like few steps to improve the separation from the discriminator. And then you do typically a single step updating generator parameters, like dragging the same kind of separation measure in the opposite direction. And in fact, you do it over and over again, and in reality, it typically yields quite good results. Although, in principle, this is quite an unstable system. And in practice, you would need to perform regularizations and improvements over this model to be able to stably train your models to get these reasonable results. But this is kind of like a different subject, so I'm not going to cover it in here. So this is what was about the generative adversarial networks. Now, as I said, I'm going to cover also these another model called operational autoencoder. Like the start of the setup here is kind of similar. As similar to what we had in GANs, we want to find a transformation from some random noise. In GANs, as you remember, we had some random noise in the input, and we wanted to transform it to real, realistically looking objects. So here we have kind of similar thing. We have this random noise Z distributed to some again some fixed distribution that you choose. It's part of your model, and then you have this data domain, like you want to map from Z to X. But if in GANs this was a deterministic transformation, like for each value of Z, we were able to transform it to some value of X using our neural network. Here, we want to parameterize it in a probabilistic manner. So essentially, we're introducing this kind of conditional distribution. We're introducing a distribution over the target objects for a given Z value. So how this can be done in like a generic way of doing this would be to introduce some closed form PDF, but the parameters for this PDF are defined by the output of some neural network, as written here. So basically, your neural networks, it takes these values of Z. These are typically called latent codes, so just latent variable, and it decodes these values into the parameters of the distribution for the X given Z. And so basically, once you have introduced this model in this form, this means that you are essentially modeling your marginalized distribution for the target objects of interest, which can be basically written as this integral of your distribution over Z, the one that you picked, and this one is fixed, times this distribution, which depends on the parameters of your neural network, and you just integrate over all values of the Z to get the marginalized distribution. Now, how would you go about training this model? So for now, let's assume that we can inverse this transformation. So by which I mean that let's say that the distribution of z given x under our model is available to us. In practice, it's typically not. But let's start from here. So this means like for each x from here, we know like the distribution of z given x corresponding to corresponding to this x. Now, if we did have this distribution in the closed form, we will be able to train our model by maximizing log likelihood in the following manner. Here I have some formulas, but the general idea here is that I can take my likelihood. So basically, this is just the log probability. I can plug examples of data in here to evaluate it and to maximize parameters with respect to maximize this value with respect to the parameters of my model. And an efficient way of doing that would be to not like here I just we have some transformations that should be all correct, and in the end you can see that this likelihood also equals to this expression here. And now here note that we can now for each of these x that we got in this model, we can sample a corresponding z if we knew this variable, and maximize likelihood only for like the z distributed to this conditional probability. So this would basically be like maximizing likelihood not for all z values, but only those z that correspond to generating this particular x. And in the same time, we would also want to maximize the entropy of this conditional distribution, which is basically means placing high probability mass on as many z values as that could have generated this particular object x. But as I said, in practice, we typically do not have this. It's called posterior distribution. So we can try to approximate it with some other distribution, and again, we can parameterize it with some parameters. And so this can be done in exactly similar way as shown before with a neural network, where you just set some distribution and set its parameters to the outputs of another neural network, and this other neural network would be our encoder, as it encodes the actual objects to the latent codes z. So if you do so, if you just replace, so here this expression is the same way as we had on the previous slide. We just replaced this exact posterior with our approximation, and so if you do so, you can show that the resulting expression is a lower bound on the true likelihood log p. Oops, sorry, log p. And so if you maximize this expression, you will in turn maximize the actual likelihood itself. And in fact, you can even show that the difference between this thing and the true likelihood just equals to the Kullback-Leibler divergence between your approximation and the true posterior. So if your family of approximation contains the true posterior, then this optimization will eventually give you the true optimum. And then this particular form is not very friendly to optimize, but you can really just play around with these logarithms and rewrite it in a different form shown here. So this is basically the optimization measure that's optimized in the variational autoencoders. And so what's nice about autoencoders is that you can optimize. This is just a regular optimization. There is no such instabilities as you have with GANs. This expression you can typically just calculate in analytic form, and this is just your likelihood for some given particular object x. Yeah, so this is all about the introduction I wanted to give. Now looks like I've been spending quite a lot of time, so I'll quickly go through some of the applications that have appeared recently. So application of these models in hydrogen physics is quite a developing field. And so this is, for example, a paper from a year ago, which discusses the applicability, like how some systematic uncertainties arise when you use this kind of models for fast simulation. And only there they had like many references, and I'm sure there could have been even more. So I'm here just cherry picking just a few applications. So like this one was the one where it all started, the very first application was basically a demonstration that you can take jet images and try to train a neural network, trying to train again to reproduce, to generate similar images. Yeah, so probably going to go a bit more quicker. Like this second work I'm picking up here is by the same authors. This was the application of similar techniques to generate calorimeter signals. So here, what's interesting is so here they only measured how much faster they are performing comparing to the Giant-4 simulation, and on CPU it was like 10 to the 3 orders of magnitudes, and for if you use GPUs, it's like 5 orders of magnitude faster compared to Giant-4. Also, what's another interesting thing is that to validate these models, they tried to look at some physically motivated variables, one-dimensional distributions, and although in some cases the reproduction is not very there are some disagreements, it's important to note that the model did not see these quantities at the training time. It only saw the individual values of these pixels. And so from individual values of these pixels, it learned learned well enough to be able to reproduce some of these dependencies, which is nice. Now, this is a work from my colleagues. They are applying similar techniques for LHCb Calorimeter. And here it's quite similar. They also, to evaluate this model, they compare like one-dimensional characteristics, even though their model produces these like images of calorimeter responses, and still some of them look quite well. There are some discrepancies, but still it's impressive how the model was able to learn these features without even seeing them explicitly. Here's a work by myself and colleagues. We were using also again to simulate Cherenkov detectors at LHCb. What's notable about this one is that here I think that this was, at least for the best of my knowledge, this is the first time that these kind of models were used with the real data. So we developed this in a data-driven manner. So we took calibration samples, and in order to separate background and signal, we had to use background subtraction using splot. So our events were all weighted, and we used those weights in our optimization measures. And another work also by myself and colleagues is about fast simulation for time projection chamber. So this particular is interesting is that due to the fact that, well, time projection chamber is this kind of cylindrical volume, that this is a tracker, like tracks passing through this volume in an ionizing gas, which electrons drift towards these end-cap planes. And in the end, you have this pad plane. This is like a series of pads of sensitive elements, and we wanted to simulate the responses of these pads to different tracks passing through this volume. So to do that, we in fact simulated like responses in small patches, in small patches of these pads, conditioned on the parameters of the track. And here we were kind of proud of how well it ended up. Like the tracking characteristics we got are spot on. If you check out our publication, there are some other measures that were a bit worse, like there is momentum resolution that was a bit worse, but we understand why this is happening, and we expect to improve this result. And it will be quite ready for usage.
I'm sorry, you are almost out of time, so please.
Yeah, sure. I'm going to wrap up now. So I'm going to skip this one. Well, in fact, it's there's quite a lot of works, and if you are interested to have a look, just check out, for example, this webpage. There is a nice list of such works. Yeah, I guess I'm gonna skip this one as well. So then the summary will be just that I hope I was able to show you that generative models are an exciting and very quickly developing field of machine learning, and these models promise to be quite good candidates for fast simulation models in high-energy physics. In this talk, I was only able to cover GANs and variational autoencoders, but there is much like there are other models based on normalizing flows and mixture models, which I wasn't able to cover here at all. And I kind of hope to have some small discussion about performance evaluation. Also, didn't get time, sorry about that. But like the bottom line is typically quite tricky to evaluate the performance. So there are a lot of open questions about how to do this properly. But yeah, thank you very much for your attention. I'll be happy to answer any questions if there are.
Okay, are there any questions? Okay, let me ask you. You were talking about generative models. Do you use also parameterized generative models, like, for example, you want not just simulate some particular event, but event with some particular properties, for example, energy or whatever?
Yeah, everything I was like, yeah, I had to like skip on the details, but everything, like, for example, if we talk about this work, your generator, when it generates this outcomes of a calorimeter, it takes also as an input the parameters of the particle for which it simulates the outcome. Same goes here, same goes like to every of these models. So this is all conditional generating.
I see. Okay, no more questions as I see. Then let us switch to next speaker.